syllabus stuff. Okay, first thing, before we even get to the syllabus, I use the hell out of Moodle in my classes. That's where all stuff goes. So there's a digital copy of the syllabus here. There is a link to our Zoom meeting. If you'll notice, we are on Zoom right now. I record all of my lectures. So that can mean multiple things, okay? One is, for those of you here watching it live, provides you an opportunity to go back and rewatch things if you didn't catch something or something like that. Two, it allows you to miss class due to illness and keep caught up by attending the class virtually. Or three, my least favorite option, but absolutely an option because you're all adults, is you can effectively take the class asynchronously because I'm recording everything as well. So what that means is I am not going to penalize anybody for not physically showing up or not virtually showing up at the right time. Your exam grades are going to do that for you. It is absolutely possible to pass and do well in my course without physically attending or anything, but you're missing out on opportunities to be able to like ask questions and clarify things and all that kind of good stuff. So do it at your own risk, but you are all adults who are paying either your or someone else's money to be here. If you want to waste that, that's your prerogative. Doesn't bother me either way. I get paid the same regardless if there's 1 of you or 40 of you. So I also have a link to virtual office hours here. If you don't feel like coming up to campus during my office hours, you can reach me over Zoom during my office hours times. And then another link down here is for a homework formatting example because I am an asshole and I want my homework turned to me in a very, very specific way. If you don't do it that way, you get a 0. So I'll give you an example of what I want, and we'll talk about that more in depth in a moment. All right, so syllabus stuff. Let's see if I can't make this a little larger. All right. This is circuits 2. To the best of my knowledge, all of you have passed circuits 1 and are supposed to be here now. I'm Dr. Hartman. My office is upstairs here in Nethkin Hall. My office hours are Tuesdays and Thursdays from 10 to noon and from 1:30 to 4:30 p.m. In addition to these 10 hours a week, I'm available to answer your questions. Eta Kappa Nu, which is the Electrical Engineering Honor Society, of which I am its faculty advisor, offers free circuit tutoring on Monday and Wednesday evenings here in Nethkin Hall, room 105, from 4:30 p.m. until 5:30 p.m. My email address is my last name @latech.edu, and there's my office phone number, which I don't answer. So if you need to reach me, either physically come hunt me down or send me an email. In the event that, I don't know, the shit hits the fan, we're going to go fully online using Moodle and Zoom and all that kind of stuff. Connor. Monday and Wednesday, 4:30 to 5:30. Nethkin room 105. So when you leave here, go down the hallway to your left and pretty much keep going until you find me. I want to say it's the room that you took circuits in a couple of summers ago, actually, if I'm remembering correctly. All right, our course objectives are to apply the knowledge we learned in circuits 1 to more difficult things effectively. The textbook and reading material, unofficially, it is Engineering Circuit Analysis 9th edition by Hike, Kimmerly, and Durbin. I don't particularly care if you buy this book or literally any book for this class because all of my lectures and all that kind of stuff will be posted online. For those of you who didn't have me for circuits 1, if you're just itching to get a circuit analysis textbook, if you go to Google and type in CADULABY, the first thing that pops up is a free textbook written by some faculty at the University of Michigan, Berkeley, and Utah. In my opinion, this is a very good book, and it is especially good because it is actually free. You're not stealing money from anybody or anything like that. It's literally just a free textbook online that has a lot of circuit analysis topics covered. So if you're going to get a book, I would suggest this one because it costs you $0. Let's see, disability disclosure thing. All right, so if you have a diagnosed learning disability or whatever, and you need classroom accommodations like extra time, quiet room, etc., let TDS and me know, and then we'll get everything in place to accommodate you as best we can. I would highly encourage you that if this is option is available to you, that you exercise it now. Don't wait and see how you do on an exam or two. Go ahead and take care of this and use the accommodations that you are entitled to. Regarding the classroom attendance, I feel like we pretty much already covered that. I don't have any preference as to whether you attend class physically, virtually, synchronously, or virtually asynchronously. It's entirely up to whatever best suits you and your work schedule or family schedule or whatever. Academic misconduct, generally speaking, don't cheat and be less rude than I am, and we'll all be okay. Homeworks, okay. So there's going to be a good amount of homework in this class, probably somewhere between 16 and 20 sets of homework. All right, somewhere between 2 to 5 questions on each set. They will be posted on our Moodle page at the end of most lectures and are to be submitted electronically. So if we pop over to Moodle here, and you guys can't actually see any of these yet, but I'll open them up as is necessary. I have online submission portals for literally every homework assignment we're going to have in this class set up. They are set up in such a way as to accept a single PDF file, okay? So I don't want 13 different PDF files, or I don't want any docx files or anything like that, only PDFs. I will not accept a paper homework. For those of you that have been in my office, the reason is pretty obvious. I have paper and crap strewn about all over the place, and it's way too easy for me to accidentally lose or misplace stuff. If you submit it digitally, I have a record and a timestamp of when you got it to me, and I know exactly where it is. So that's how I want the homeworks. Let's see. The homework assignments will be due at 5 p.m. 1 week after they're assigned and must be properly formatted as detailed in this homework formatting example. So I'm going to tell you exactly how I want your homework, okay? The first page or pages will literally be the assignment sheet that I provide to you. I'm going to give you a digital copy of it in docx format. If you need to, type your name or whatever in, that's fine. So your first page or pages will be the assignment sheet itself. So for this particular homework set, it looks like the first 4 pages were just the assignment sheet. Then I have my handwritten work for problem 1, which is in engineering format, meaning you give me the problem statement, then you start your solution. I do not have a preference as to whether or not you physically write the problem statement down, or you just put a digital copy of it and then start working it underneath there. I always wrote it down, but I don't care whether or not you do. But I do want problem statement and then solution. I do not need what's the thing at the end of your freshman homeworks where they're like a discussion or whatever? Yeah, it's because math or because circuits work this way. I don't need a discussion or anything like that. Just give me the problem statement and then the solution. Now, we go through a couple of pages here. Let's see, page down. There we go. More page down. Even more page down, because apparently it took me several sheets of paper to solve this one problem. There we go. After this, I have my MathCAD work, okay? MathCAD is not required to solve all of the problems in this class. It's going to be used for a lot of them, but not all of them, okay? So if you can solve the problem without using MathCAD, meaning that you can solve it using a standard FE approved calculator, you do not need to include any computer related work that you had to do to solve the problem. If you had to use a computer to solve it, I want to see what you did, okay? So here we have MathCAD work and all that kind of stuff. So to recap so far, we have our assignment sheet as a cover page or cover pages. Then we have the handwritten work for problem 1. Then we have the computer work for problem 1. Next will be the handwritten work for problem 2, and then the computer work for problem 2, and then the handwritten work for problem 3, and then the computer work for problem 3, etc., etc. Is that clear? Is it in any way, shape, or form confusing? I'm asking this because I guarantee at least 3 of you are going to manage to screw it up. Okay, Connor.
It is crystal clear. Just want to make sure for attaching diagrams, can we just snip spice diagrams in there?
For sure, absolutely. Okay, so that's a fantastic question, bringing up the concept of spice. I don't know that it's mentioned anywhere on the syllabus, but let me go back to Moodle here. And if we go here into class meeting 1, there's a link for a computer program called LT Spice 17. And then a link, so this is where you can download it. This is a link that kind of tells you what it does. This is a link that has some tutorials that somebody else developed. We are going to use LT Spice extensively in this class. This is a circuit simulation tool. We're actually going to use it today. That's kind of the topic of today's lecture after we wrap up all the syllabus stuff. Some of you may be asking yourself, well, why didn't we learn how to do any of the circuit simulation stuff in circuits 1? And the short answer is because WebWork has no way to check your work. You could just use LT Spice to generate practically every answer you ever needed. It is a very powerful tool that can do multiple types of analyses, and we are going to use it to do DC operating point analyses, transient analyses, and frequency domain analyses. It can be used for 3-phase power analysis and all that kind of good stuff too. Effectively, it can be used for literally everything that we do in this class as a means to, kind of check your answers and make sure you're doing things correctly, assuming that you know how to simulate what it is that you're trying to figure out. Okay? So we are going to be using this extensively. It's not always going to be a required portion of your homework, but it's going to be a required portion of several of your homework assignments. Okay. So before the next class meeting, or now if you have your laptop out, while I'm just ranting about syllabus related stuff, go ahead and download this guy. All right. Okay. Any homework assignment submission that does not adhere to the format detailed on our Moodle page will be rejected from grading in bold, meaning you give it to me the way that I want, or you take a 0. It's a binary decision. Okay, it's either correct and I will grade it, or it's incorrect and you get a 0. If you submit a late homework assignment, you will get a 20% penalty for each day they're late. So on Moodle, on the online submission portal thing, it literally tells me when you turn it in and how either early it was, so before the due date, or how late it was past the due date. So effectively what I'm going to do is I'm going to look and I'm going to say, okay, so this says that it's 17 seconds late. Well, that's late. So you get 20% off, or it's 1 day and 7 hours late. So that's 40% off, etc. Okay. Everything is time stamped so that I can know whether or not to incur a late penalty upon you. Design projects. There will be a few design projects as part of this class. Each project will require some handwritten analysis and then a supporting simulation to show me that your circuit that you've designed should behave in the way that you should expect. If you don't complete all of the design project assignments, you fail. Exams. There are going to be 4 exams given during this course. Each exam consists of a closed book, and I say closed notes, but honestly, most of the time I either allow you an equation sheet or provide you an equation sheet for some of the tests. So it's 75% in class, and then it's 25% take-home test. So effectively, the in-class problems are, I would say, of the difficulty of what you saw for your circuits 1 problems, except that now partial credit is a thing and stuff like that. They're not multiple choice exams, okay? So you just work out the problem, and whatever you get right, you get credit for, and whatever you get wrong, you don't get credit for, all that kind of good stuff. And then there will be take-home portions where I'm going to ask you harder problems that necessitate the use of computer analysis, okay? So the expectation for the take-home portion is that everything is fair game except your peers, right? You can absolutely use, open notes, open book, open internet, all that kind of good stuff. What I don't want is Dylan and Connor colluding. I say this because I've had in the past students taking the take-home portion of my exams, and we're dumb enough to talk about it to each other in the grid, literally right over there, within earshot of me. So if you're going to cheat, don't be that damn dumb. Don't do it literally in the building that I'm in, where I could walk by at any given time and catch you. Okay. Just saying. Exercise some form of intelligence. All right. Only FE approved calculators are permitted for use during the in-class portion of the exams. So that's your TI-30s, TI-36s, Casio 115s, Casio 991s. And there's a couple of HPs that are allowed as well, but I've never actually seen somebody use one of those. So if your cell phone goes off during your test, congratulations, you failed. All right, so the weighting of the grades is as follows. Homework is 20%, so that means 2-letter grades is dedicated to homework. If you're one of those people that doesn't care to do homework, the best you can do in this class is a C. So I would suggest getting over that aversion to homework quick, fast, and in a hurry. The design projects are 10% of your final grade. Earlier, I said that if you don't do them, you fail. So literally turn something in that shows you tried, okay? Because these are used for our ABET accreditation. So I need something to show that students are trying to learn how to pursue engineering design. Exams 1, 2, 3, and 4 are all worth 20%. And whichever exam you score the worst on, the weight of that exam is reduced to 10%. So that comes up to a total of 20 plus 10 is 30. And then 30%, or excuse me, 60% for the 3 exams you score the highest on, bringing us up to 90%, and then 10% for the exam you score the lowest on, for a total of 100%. So you can have one badish test day and it won't completely sink you in the class. The grading scale is a traditional 10-point scale where you need a 90.000 or higher to make an A. I fundamentally do not believe in curving. You either make the grade or you don't. The contents of this syllabus are not expected to change, but if I need to, I'll do so, and I'll let you know what changes were made. And then our emergency notification system stuff, effectively, you should be signed up for it by now. If you're not, there's a link. Regarding the COVID policy, All the information is available online. In short, if you're sick, don't show up and get me sick or I'm going to be furious. So do not get me ill. All right, any questions regarding the syllabus? Okie dokie. So what I want us to do today, we're going to do some what I hope should be fairly straightforward circuit analysis. And then we are going to simulate that circuit to verify that our analytical results match those of the simulation. So I am teaching you how to check your answers using LT Spice. For the overwhelming majority of the homework assignments, there should be no reason you ever don't get 100 because I'm teaching you how to use the tool that tells you whether or not you got the answer correct or incorrect. All right. Excuse me. So the circuit that we are going to analyze is one that I put on a Circuits 1 exam a while back that several students didn't do particularly well on. So our circuit of interest today is this guy, where we have a 2-amp source connected in parallel to an 18 ohm resistor. Connected in parallel, excuse me, that's not in parallel, connected to a 3 ohm resistor. And then I have the bane of most of you guys' existence, a dependent source providing a voltage of 4 Vx. Here we have a 16 ohm resistor, a 10 ohm resistor. Here's a 3-amp source, direction down. And then up top here, we will have a 7 ohm resistor. And the voltage Vx is defined to be the voltage drop over the 7 ohm resistor with positive polarity terminal on the right. On the exam, I asked 3 questions regarding this circuit. The first question was, the voltage Vx is closest to something. We're just going to solve for it. The second question I asked was the power absorbed by the 2-amp source is closest to whatever. And then finally, the power supplied by the dependent source is closest to, we're just going to solve for that quantity. So the first question that we should ask ourselves is, what circuit analysis method do we want to employ to determine these 3 quantities? Charles, what are your thoughts? Nodal analysis. Sounds great to me. I personally would also do nodal analysis because there are 3 nodes. If I choose the bottom as my reference node, I mean, there's 4 nodes, but one of them is going to be a reference node. So it's a 3 equation, 3 unknown system. Whereas if we did mesh analysis, there are obviously 5 meshes. We could simplify the circuit by doing source transformations on each of these wings outside, eliminating some meshes. But nodal analysis gets us the answer with the least amount of effort. So that's the way that I'm going to approach it. So I am arbitrarily going to say that my bottom node is my reference node. And then this top left node, I'm going to call node A with an associated nodal voltage VA. This middle node will be VB. And then this top right node, or right node, will have an associated nodal voltage of VC. All right, so since we're using nodal analysis, we have a voltage source, which means we're going to need a voltage relationship equation. And we have a dependent source, which means we're going to need a controlling variable equation, right? So let's start with our voltage relationship equation. Connor, I'm going to pick on you. How do I express this voltage for Vx being provided by my dependent source in terms of my nodal voltages? And I'm picking on you for this specifically because I know it's been forever since you took circuits 1.
Equivalent to VB.
That's correct. Absolutely right. So our first equation is 4Vx is equal to VB. Our controlling variable relationship Skylar, how do I express this Vx, the voltage drop over my 7 ohm resistor, in terms of my nodal voltages? VC minus VA, absolutely correct. And from this, I can substitute my controlling variable relationship into my voltage relationship. And this is going to give me an equation negative 4 VA minus VB plus 4 VC is equal to 0. I'm just going to call this equation 1. So I smashed these 2 equations together and reorganized to get that guy. Everybody okay with my use of algebra there? All right. So we got the easily forgettable things out of the way. Now all we need to do is apply KCL at node A and KCL at node C, and we have enough information to determine all of the unknown voltages in this circuit, where we don't have to apply KCL at node B because our supernode around our voltage source, 4Vx, contains our reference. So anytime it contains a reference, again, we do not apply KCL. So Elijah, what should my KCL equation at node A be? Negative 2 amps, all right. VA over 18, I'm good. I disagree with that. VA minus VB over 3 ohms. And then what about the path up through the 7 ohm resistor? Exactly right. So we'll have negative 2 amps plus VA over 18 ohms plus VA minus VB over 3 ohms plus VA minus VC over 7 ohms is equal to 0. Let's call this guy equation 2. And then we'll do KCL at node C. Catherine, what's that going to look like? I can't hear anything. I'm old. Okay, so 3 amps is leaving, so I agree with that. VC over 10, I agree with that. I agree with that. And what's the part that goes up and through the 7 ohm resistor? Exactly right. Either I'm getting lucky on who I'm calling on, or you guys actually learn things in circuits 1. So we have 3 amps plus VC over 10 ohms plus VC minus VB over 16 ohms plus VC minus VA over 7 ohms is equal to 0. Let's call that equation 3. And we can solve these guys for the voltages VA, VB, and VC. And in doing so, we should get negative 16.158 volts, negative 22.825 volts, and negative 22.224 volts. From this, Vx, which I believe Skylar told us earlier was simply VC minus VA, comes out to be negative 5.706 volts. So that would be the answer to part A in a pretty straightforward fashion. Parts B and C, we're going to have to do some thinking about. Okay. So the power absorbed by the 2 amp source. So if we want the power absorbed by the 2 amp source, we need to know the current that's being supplied by the 2 amp source and the voltage drop across the 2 amp source. Connor.
The supernode is just one that includes the voltage source.
Yep, that's it.
I'm sorry, could we go back to the solution?
Let me know when we can get back to analyzing things. All right. So as I was saying a moment ago, we're trying to determine the power absorbed by the 2 amp source. Since it's a source, we need to know both the voltage drop across the source and the current flowing through the source. Since it's a current source, the current flowing through it is rather trivial. The voltage drop across it is slightly less trivial because we need to pay attention to the polarity that we want, right? So since we're looking for the power absorbed by the 2 amp source, we want the current flowing into the positive polarity terminal. So I would argue that we are looking for this voltage, which I'm going to call V 2 amps. So that the current flows into the positive polarity terminal, and the product of V 2 amps times this 2 amps gives us the power absorbed. Everybody okay with that? How does that voltage V 2 amps relate to our known nodal voltages? Is it VA? I disagree. Negative VA. That's right. So P2A is just going to be 2 amps times negative VA, which I get to be 33.035 watts. And then the last question specifically asked for us to find the power. I think it was supplied by our dependent source. So let's look at what's going on there. Okay, so it is a power supply. Again, since we have a source, we want the voltage drop across the source, which is provided to us, and the current flowing through the source. Because we're trying to find supplied power, we want the current that is flowing into the negative polarity terminal. So I'm going to write that like this. I dependent applying Kirchhoff's current law at node B is simply the current that branches off and flows to the left through the 3 ohm resistor added to the current that branches off and flows to the right through the 16 ohm resistor. Everybody okay with that analysis? So from that, E dependent is 4 Vx, so 4 Vc minus Va. And then the current that flows to the left was Vb minus Va over 3 ohms. And the current that branched off and flowed to the right was Vb minus Vc over 16 ohms, giving me an answer of 48.486 watts. That's the amount of power supplied by our dependent source. All right, so anybody have any problems with that analysis? Hopefully everything is straightforward. This literally should have been a review. Here comes the not review part. Putting this guy into LT Spice and seeing that our simulation matches that of our analytical analysis. Fully understand that not all of you have downloaded LT Spice or anything like that. So if you just kind of pay attention to what's going on, this is literally all being recorded and you can refer back to this at your leisure. Okay. So I'm going to open up a new schematic. And up here is effectively where all my tools are. Okay. So I'm going to talk about a couple of things here real quick. The pencil is how we draw. Shut up, watch. The pencil is how we draw wires. Okay, it's how we connect the terminals of resistors, capacitors, inductors, voltage sources, transistors, all that kind of stuff to other elements. This symbol here is just a wire with a triangle that's pointed down, is how we establish ground. LT Spice uses effectively nodal analysis for all of its analysis. So regardless of the type of circuit that we are trying to analyze, we have to set a node as ground. If we do not set a node as ground, LT Spice will tell us that we have to do that in order for it to do any analysis. This guy to the right of the ground symbol, it looks like a little sign, is effectively, I can't remember what its exact name is, but it's how we give names to specific nodes and things like that. Okay, so it's really just for bookkeeping and labeling things. The resistor symbol is how we can put down resistors. The capacitor symbol is for capacitors. And the inductor symbol is for inductors. Then we have a diode symbol, which you may not be familiar with, obviously for putting down diodes. And then we have this symbol right here, which actually looks like a digital logic gate. This is the general component menu where we can select anything that we have available to us. Then we have move and copy and all that kind of good stuff. All right, so for my sources, I have to go into the general tab. To make my life easier, I'm going to use my keyboard. So if I want a current source, I can just type in the word current and blammo, I get a current source. Okay. So if I'm going to put the 2 amp source, I need the current source to have a direction up. And by default, I have a direction of down. So I'm going to need to rotate this guy. I rotate by pressing Control R. So Control R twice makes my current source in the direction that I want it to go. And I'm going to shrink things down because I'm going to be putting a lot of components in. Now I'm going to throw a resistor over here. And then another resistor way over here. I think that's all 5 of my resistors. And let's see, I'm going to go ahead and throw another current source over here on the right. This one should be direction down. And then I need a dependent voltage source. Okay. So LT Spice doesn't have voltage controlled voltage sources and current controlled voltage sources. Okay. It has what are called behavioral voltage sources, which you get by typing BV. So a behavioral voltage source is a catch-all dependent source where we input a mathematical expression that tells it how to behave. So it doesn't care whether it's a current controlled voltage source or a voltage controlled voltage source. We tell it what the output voltage is supposed to be. It's based on some mathematical function. So we'll get to that in a minute. I have all of my components here. So now I'm just going to wire things up. Yep. Up here, the one that looks like a digital logic gate is the general component menu. You can get resistors, capacitors, inductors, and all that kind of stuff in there. Just literally type in what you're looking for, and chances are it's in there. BV for a behavioral voltage source, and it'll be BI for a behavioral current source. All right, so we have effectively everything wired up. I'm going to go ahead and put a little stub of wire down here at the bottom and connect my ground there because that's literally where we chose our ground to be. And then I'm going to use this labeling thing here. And I'm just going to put a label of VA, and I'm going to place that on the node where I'm solving for VA. Then I'm going to do another one, call it VB, place it on the node where I was solving for VB. And a third one here, VC, which I will place on that right-hand node where I was solving for VC. Okay. Now I need to give values to all of these components. So let's start with the resistors. If I mouse over any of the resistors, my cursor changes from these crosshairs to a hand. So whenever I have the hand cursor, if I right click, it brings up a menu that will allow me to either type in my resistance value. I can also include a tolerance percentage and a power rating. So I can use LT Spice to effectively randomize things a little bit. So instead of saying I have a 5 ohm resistor, if I have a 5 ohm resistor with a 10% tolerance, it's going to give me something between 4.5 ohms and 5.5 ohms, just depending on what the simulation is. And a power rating can tell me whether or not the circuit that I'm designing is exceeding the power rating of these particular resistors. So am I or aren't I going to burn a component out? For this class, for the most part, we're just going to play around with this resistance value where it is automatically measured in ohms, so we don't need to give it units. We could actually select common resistor values and all that kind of stuff too. So the resistor that I'm changing right now is the 18 ohm resistor, so I'm going to put 18. One thing that I want to clarify here is that LT Spice can't tell the difference between lowercase letters and uppercase letters. And so what I mean by that is if we have something that's expressed in milli whatever, typically we use lowercase m. If we had something expressed in mega, we would express it uppercase m. LT Spice interprets both lowercase m and uppercase m as milli. So to get a mega something, you type MEG. Okay. So not going to come up for a bit, but it is going to be an issue. All right, so we have our 18 ohm resistor here, 3 ohm resistor here, 7 ohm resistor up top, 16 ohm resistor here, and a 10 ohm resistor here. All right, now let's deal with these current sources. So if I put my mouse over the middle of the current source, again, I get the hand icon. And my options here are to give it a DC value and then press OK, or I can cancel it, which gives it no value, or I can press the advanced tab. We're not going to use the advanced tab in this simulation, but I just kind of want to show you what this can do. And this advanced tab is the same for all of our different voltage sources, okay? So we can give it a DC value, or we can give it a pulse value. So this is effectively how we get square waves with differing duty cycles. So we tell it how long it's off, how long it's on, what the on value is, how long it takes to transition from on to off, how long it takes to transition from off to on, what the period is, how many cycles we want, all that kind of good stuff. So these are the different parameters for pulse. We can also do sine waves where we can give it a DC offset. Then we have our AC amplitude. We tell it the frequency in hertz. So we don't have access to omega, the angular frequency. We only have access to F, the linear frequency. That's a very important thing here. T delay tells it how long to wait before the device turns on. I don't remember what theta is. Phi is the phase angle, and we can tell it how many cycles that we want. LT Spice expresses sinusoids as sine functions explicitly, okay? So if we want a cosine function, we need to put a phase angle of -90 degrees. And again, the frequency is expressed in hertz, not in radians per second. So if we wanted, let's say 100 radians per second, we have to put 100 over 2 pi in this box to get what we want. Bradley, you were raising your hand.
Sorry, I wanted to ask how you put the DC.
Okay.
Just text or was that?
All right, so just a moment here. Let me cancel this out. Cancel that out. Anytime I'm labeling something, I'm using this button up here, which is to the right of the ground button. All right. I can do exponential voltage and current waveform. So I give it some initial current, the value that it's going to hit, how long it takes it to go up, and then the time constant, how long it takes it to go down, and then the time constant for the decay as well. So pretty powerful. I use this in my simulations for work a lot. SFFM is used in communication systems where you're doing frequency modulation and all that kind of good stuff. So you can tell it your carrier frequency, your modulation index, DC offset, all that kind of good stuff on top of it. So you can do some software-defined radio simulations and all that kind of stuff in here. Then we have PWL. That's effectively just playing connect the dots. So it's just using linear line elements a combination of linear elements to make any signal that you could want, where you could put in things specifically, or you could literally just upload a file. And then finally, you have the option of literally uploading a table of voltages where it'll just give you that. In this class, we're going to use pulse and sine, as well as DC. And then over here on the right-hand side, when we do some of our frequency domain analysis, we'll use this stuff over here. I'll tell you when we're going to use it, and we're going to use LT Spice and examples in class and all that kind of stuff. All right, so let's just back out of this. We'll give this a DC value of 2 amps. Over here, we need a DC value of 3 amps. And our last thing is probably the most tricky. This is our voltage controlled voltage source. So what we're going to do is we're going to right click the line where it has V is equal to F dot dot dot, which is simply saying the voltage is equal to a function. We just have to put the function in. So in this case, our function is 4 multiplied by, and I'm going to open parentheses here. So we want the voltage, which we indicate with a V, of the node VC minus the voltage of VA. Okay. So let me explain that here real quick. This VC does not say, I want the voltage at node C. This is a label saying that this node is now called VC. This node is now called VA or VB, and this node is now called VA. So this mathematical expression right here says we have 4 times the voltage measured at node VC minus the voltage measured at node VA. Is the syntax on that statement clear? All right, so finally we are ready to simulate. If we press the simulate button, let's just press run, and it's going to tell us we need to tell it what kind of simulation to run. We have several different options. The option that it defaults to is transient analysis, which simply means that we're going to be looking at how waveforms change as a function of time. Okay. Then we have AC analysis, which is going to look at how the circuit behaves as the frequency changes. Then we have a DC sweep, which will let us change different parameters, so different DC values. Then we have a noise analysis, which has nothing to do with this class. DC transfer functions, which has nothing to do with this class. And then DC operating point. Since this is a DC circuit, we're going to look at its DC operating point. There are no parameters for this. It just does the math and then spits stuff out. So I'm going to press OK. Oh, oops. I don't know. I thought I put 2 in there and it said it's a sine function, so I'm a little bit confused. 2. Okay. Let's run this. All right. And then it just gives me a box. It tells me the voltage at node VA is this, the voltage at node VC is this, the voltage at node VB is this, and then the current through my behavioral source is this, the current through the current source labeled I2 is 3 amps, current through this is 2, etc. Then it gives me all my resistor currents and all that kind of good stuff. Bradley.
So it's saying unknown variable V. Whenever I put the VA,
We'll do that at the end.
I need to watch it.
Okay, just pay attention to what I'm doing. I'll help you when we finish up. Okay. So if I close out of this, like so this is a menu that just has all of the different things that were calculated in our simulation. Okay. I'm going to close out of this. Now my cursor is effectively a probe. All right. So if I mouse over a node, down here in the bottom left, it says this is node VC because I gave it that label. The DC operating point voltage is negative 22.22 3909 volts, which absolutely matches what we found earlier. Any node I mouse over, it will tell me what that nodal voltage is, okay? So obviously Vx, I would just get by taking the voltage at node Vc and subtracting from that the voltage at node Va. Now for currents, if I mouse over a component, it tells me the DC operating point current for this particular resistor is 37.57 to 1158 milliamps. And then it has a dissipation. So not only does it tell me the current flowing through the element, it also tells me the power being absorbed by the element. So if I mouse over the 2 amp source, the power being absorbed is 33.03529 watts, which absolutely matches the analysis we did. If I mouse over the dependent source, the power absorbed is negative 48.846 and change, which is positive 48.846 and change watts supplied. All of the answers to the questions that I asked can be gotten by using this operating point analysis and then literally mousing over the quantities that we are interested in. Okay. Now, one thing that is mildly annoying is that when I mouse over a resistor, it tells me the value of the current, or actually if I mouse over any element, it tells me the value of the current, but it does not tell me the direction, okay? That's a little bit of a problem because sometimes we're going to be setting up behavioral or dependent sources that depend on a value of current, and the direction of that current is very important to that. If I delete my operating point analysis and change it to a transient analysis, let's just run it for 1 second, just for the sake of argument. It gives me a blank graph because I haven't told it what I want to measure, okay? Now, if I were to click on this nodal voltage, I'm going to get a straight line because it's a DC voltage. That's not really what's important here, what I'm trying to illustrate. When I mouse over an element after I've performed a transient analysis, I get a current probe that literally has an arrow telling me the direction of current flow. Okay. If I mouse over a node, I get a voltage probe. Doesn't tell me anything about, well, actually it does. It gives me my DC operating point information and all that kind of good stuff. So it's telling me that this guy is dissipating 15.157 watts, all that kind of stuff, but now it's telling me specifically my current of 917.647, or excuse me, negative 917.647 milliamps has a direction down. So obviously direction up, it would be positive 917. So chances are you're going to wind up using a combination of DC operating point analyses and transient analyses in order to figure out directions of currents and all that kind of good stuff when they're necessary. All right, so I think that is enough out of me for today. Like I said, all of this has been recorded. I will upload it probably later this afternoon for those of you that want to play around with LT Spice and all that kind of good stuff, and follow along if you weren't able to do so. All right, anybody have any questions other than Bradley, who I'm going to talk to in a minute?
I didn't quite hear you when you said, so you simulate and then run and then DC sweep. So.
No. Okay, so for this particular circuit, our first analysis was a DC operating point analysis. DC sweep, if we click there, we have different, effectively what we can do is sweep our sources to make them have different values and then see how things change. Since we had a DC circuit where literally nothing was intending to change, we did a DC operating point analysis. Yep.
For the training analysis, what about putting a stop time or?
Leave it blank. Leave it blank. Yeah. So let me show you literally exactly what I did. Oh, sorry, you don't leave the stop time blank because you need to tell it when to stop, but everything else, I left it all blank. Now, there will be times, like if we were doing an analysis of a circuit, transient analysis of a circuit that is operating at like hundreds of kilohertz or something like that, we might have to play around with the maximum time step and stuff like that to make sure that our signals are actually looking sinusoidal. Because if we don't make that specification, we'll get like a funky looking waveform because it's sampling it poorly. So we have to tell it how many times we want it to be sampled per cycle effectively. Not really going to be much of an issue. Yeah, so for the most part in this class, we're usually just going to give it a stop time to tell it when to stop taking measurements. Yeah. So 1 just means 1 second. 1 M means 1 millisecond. 1 U means 1 microsecond. 1 N means 1 nanosecond, etc. Since this is a DC circuit, it literally doesn't matter what value I put in there at all. So I just gave it an arbitrary number. But for when we're doing like transient analysis of RL, RC, and RLC circuits, telling it when to stop is important because we are trying to look for changes. So if we had a circuit that had a time constant of, let's say, 1 millisecond, and we looked at it over a time span of 5 seconds, we wouldn't really see any of the transient analysis because it would occur so quickly that we wouldn't catch it. So if we had a time constant of, say, 1 millisecond, our best bet would be to look at it only for a time of, say, 5 to 10 milliseconds so that we can actually see what's happening. But we'll talk more about that when we start looking at circuits that aren't DC, which will be Friday. After class on Friday. Yeah. So today is just play around with stuff there. Any other questions? All right, see you guys on Friday.